Okay, good morning, everyone. Um, the title of my report is Robot Assisted Personalized Upline Rehabilitation Training based on reachable workspace. My name is Bai Jing. Uh, I'm from Nanjing Institute of Technology. This is the contents. Let's begin with the background. The number of patients with hemiplegia caused by stroke have increased, which seriously affects their daily life activities and brings heavy burden to their families and the society. The stroke lead to paralysis, death, and need treatment costs. Robots can provide scientific and effective rehabilitation training methods with the advantages of good strength, persistence, and repetitiveness. The repetitiveness for the length, strength, range of motion, and the moment velocity of the affected limbs of different patients is different. How to evaluate the degree of the affected limb quantitatively? Uh, develop personalized training methods. This is a serious problem faced by robots in assisting rehabilitation training without the supervision of doctors. Quantitative assignment can get the design and the training method of the robots, uh, so that it can meet the individual needs of different patients. Current assignment methods such as brainstorm states and so on. The process is time-consuming, labor-intensive, and inconsistent consistent in judgment. In judgment. Mm. In judgment criteria, robots can provide objective and precise measurements of patient behavior, but it's extremely vulnerable to its workspace constraints. So the combination of visual equipment and robots can solve the problem of space limitation and realize quantitative rehabilitation assignments and training. Uh, some scholars have conducted research on assessment methods as follows. And the connector is a market tool that can realize human target detection and tracking and can be used for reputation training of stroke patients. Some researchers use this tool to do the assessment. This is the highlights. The upline rehabilitation training method based on workspace is proposed to meet the individual needs of patients. The kinematic model of upper limb provides the patient's ability and visual motion to the controller. Variable impedance control combined with non-parametric potential field function is used to achieve personalized training. And this is the system diagram. The subject sits in Kinect's field of vision, and the connector is used to measure the position of the subject joint. The reachable space is calculated, and the robot's workspace is appropriate to the space of the subject. Then, through the variable impedance control based on non-linear potential field function, the robot-assisted personalized repetitive training is finally realized. This is the kinematics of the upline. we established a non-DF series motion model. This is the inverse kinematics. The numerical integration method is used to solve the inverse kinematics of the up limb, and RM is used for optimization. This is the equations we used. We used this to calculate the RSA. According to the trajectory of the up extremity, the sphere is fitted by the least square method to determine the parameters of the working space sphere. Then the trajectory dates are projected into the spherical coordinate system, and the maximum boundary of the trajectory is determined by the alpha shape geometry. And cadmium splines are applied to the to smooth the boundary. Next, our information is projected back into Cartesian coordinates to extract the RSA. This is the robot control. The non-parametric potential field function is used combined with the reachable workspace. The position and impedance of robots are obtained from the gradient and curvature of the potential function. Based on the demonstration trajectory, the robot provides the same assistance to the patient as the therapist. This is the equations we use in the robot control. The energy element U quantifies the attraction from XR to SP. As this equation, Gauss kernel regression is used to establish the total potential energy function. The total energy at XR is as this equation. The control law is defined as the negative gradient of U minus the dispersive field kappa. The tau is the actual force attracted to the reference trajectory at XR. This is the experiment as a figure. This is the experiment. The subject sat in front of the robot. The affected hand grasped the handle. The robot pulled the affected limb for personalized assisted rehabilitation training. This is the workspace result. The up-limb workspace is divided into 4 quadrants. Taking right up-limb as an example, the division results are shown in Figure A. The division of the quadrant. Figure B shows the RSA of the subject, and the RSA of healthy people is a ball. This is the experimental results. The figure A is the reference path. The subject's reachable workspace and the position of the end effector. The dashed line is the surface demonstration trajectory. The last sphere surface is the motion range of the up limbs of healthy people. During patient's rehabilitation training, when the patient moves within the reachable workspace, the robot doesn't provide axial force. When the movement range exceeds the reachable space, the robot pulls the end of the affected limb to the point close it to the reference trajectory. When the end effector position exceeds the reachable workspace, the robot arm applies all applies an auxiliary force. At this time, the force on the hand is measured as by a three-dimensional force sensor, and the result is shown in the red figure in this figure. Then this is the conclusion. A non-dual upper limb kinematic model is proposed based on the algorithm combining LM and the space vector method. Through the combination of upper limb reachable physics and non-linear potential field function, personalized rehabilitation training is designed to meet the needs of different patients. The experimental results show that the robot can adjust the size of the auxiliary force through the workspace of upper limbs. That's all. Thank you.